Great. So here I have DanBoneh, whom some of you I hope know, fellow faculty, in fact senior to me in the department, who researches cryptography and security. So Dan, how did you get into cryptography and security in computer systems?
Well, first
So
of all,
what's your background?
Oh, thanks, Phil. First of all, it's a pleasure to do this. I'm happy to help the class. Let's see. I fell in love with crypto at a very, very young age. I think it's one of these things where, like, for God knows why, but like my dad, for some reason, taught me the RSA algorithm when I was like 9 years old. And I just got completely fascinated by this. You know, these big numbers, and all of a sudden there are these codes. And then I went and kind of encrypted a message to my friend with RSA, and he thought I was completely nuts. But that kind of stuck with me. And then as I got to college and I learned more about crypto, I just realized it's such a fantastic field. You know, it's an area where you get to use really deep math. Literally, 20th century math is like as advanced as the mathematicists use in computer science gets. And at the same time, we get to use it for real-world applications. So people really do care about the results. In fact, you know, when you communicate with Google these days, the key exchange that you're doing is using what's called elliptic curve Diffie-Hellman. That is using extremely advanced mathematics, as I said, 20th century mathematics. And it's amazing. This is like people use this all day long, every day, without even realizing that they're doing it. So for me, it's just a lot of fun to kind of work in an area that involves both, you know, deep math and yet has real-world applications. I should say more broadly. I mean, I do. You know, there are two parts to my work. I work on cryptography as one half, and then I also do a lot of work on computer security more broadly. Cryptography is just a small part of computer security. The problem of securing software is much, much larger than just cryptography. And I should tell you that computer security in general is also a fantastic, fantastic area to work in. As a career path, it's a terrific career path.
Tremendous job security and security.
Yeah, you know, if I go to sleep now and you wake me up in 100 years, the first thing I'll ask is, you know, is computer security still a problem? And I guarantee you computer security will only be worse than it is today, right, because we will be depending on computers and networks so much more than we do today.
Well, so students in the class have covered actually network address translators a bit, you know, NATs, so they're wireless routers. So you've done some work on kind of the security of these wireless NATs today and some of the issues. Do you just want to say a little bit about that, sure. Some of the crazy holes that you found?
Yeah, sure. So we did a lot of work on security, for example, of embedded devices. So when you build an embedded device these days, so what is an embedded device? So I'm talking about things like security cameras, photo frames. You know, these are frames that you put on grandma's desk, and you can upload pictures to it so she can see grandkids. Photo frames, wireless, or you know, printers, routers, all of these embedded devices that need to be configured somehow. These days, they're configured through a web interface. So when companies do this, they have to kind of build a small web application that sits in the embedded device. Well, traditionally, when you build a web application, you would use, you know, Rails or Django or, you know, a LAMP stack in general. But a LAMP stack doesn't fit on a tiny little security camera, right? There's no SQL server running there. Yeah. So what they end up doing is they end up building their own web application and their, you know, their own infrastructure basically for making configuration possible. And as you, well, hopefully you will take one of our security classes, which I'll plug in just a minute.
Yeah, you teach 155.
That's right. I'll plug those in just a minute.
Yeah.
But you'll learn from those that, in fact, building a secure web application is non-trivial. It actually takes quite an effort to secure web applications, even from basic attacks, things like cross-site scripting, things like you know, request forgeries, and so on. And so we looked. We had we bought like 20 of these embedded devices, and we started looking one by one at the different web applications embedded on devices. And it turns out they basically all had various sorts of vulnerabilities, all. Again, it was basically a hardware company.
So somebody hacks my picture frame. Why should I care?
Okay. So you should really care about that, because if you're an enterprise and now one of your employees put a picture frame on their desk in their office, that picture frame is going to be connected to your corporate network.
So I'm glad I'm not an enterprise.
There you go.
Okay. So I don't care, but
so you can pretty much guess the rest, right?
Yeah, and Stanford's computer systems are hacked all the time. Right? So I'm not concerned about any more vulnerabilities.
Yeah.
Yeah, I'm not the kind of person you cater to.
I see. I see. I see. Okay. Well, anyhow, it's basically these devices are used as stepping stones into
Absolutely.
larger attacks. So if you have a security camera at home, that security camera, or even think of the Nest, like a thermostat that is controlled remotely. Those devices, if they're not properly secured, the Nest we haven't looked at, so I don't know if it's I don't know what the security status of that is. But those devices could be used as a stepping stone into a larger attack on your home network, on your corporate network.
Chink in the armor. So.
Exactly. Exactly.
Yeah.
And by the way, all the attacks, the way all the attacks work today, is basically is using stepping stones. Yeah, so they break into one machine. From that machine, they start to do a lateral traversal to try and find other machines that can be broken into. From that other machine that they've now taken control, they try to get to an administrator account, and so on and so on. They move slowly from one machine to another until they get the crown jewels, like the database or the Active Directory, and then they just dumped all the data from there, and away they go.
Well, so this past weekend there was the CS faculty retreat, and you gave a talk kind of about some of the revelations from the Snowden's leaks, etc. And one of the things you talked about is how there's might be some suggestions that certain crypto systems might be weaker than we thought. So without going into the details, kind of going forward, given what we've learned from Snowden, if I want to design a secure system, then what are there some extra steps I should take? Are there some things which we thought might be okay but aren't now, and you want to going forward do something slightly differently? Or
yeah, there are basically two advice bits to keep in mind. Well, first, there's a zeroth advice bit, which you would learn, which would get drilled into you once you take the crypto class, CS255, which is you never design your own crypto. And not only should you not design your own crypto, you should not even implement your own crypto, because I guarantee you, if you implement your own crypto, it's going to be vulnerable to timing attack, it's probably going to have bad randomness, and it's going to be vulnerable to other side channel attacks, and so on. So you should use kind of existing...
Don't innovate.
I wouldn't quite say it that way. I would say use kind of existing standards and existing open source, well-vetted implementations. So that's the zeroth rule. The first rule that I would say that's a result of the revelations from the summer is make sure that whatever you build is agile, in the sense that it's crypto agile, in the sense that if we discover at some point that there's a vulnerability in a particular algorithm, it's not going to take you 6 months to then go ahead and under fire, go ahead and build a new crypto algorithm into your system, QA test it, and then deploy it. That's it's a long process, which when you do under fire is a bad idea from a security point of view. The idea is to kind of make your system agile to begin with, crypto agile to begin with, so that the system will support multiple algorithms at deployment time. And then if one algorithm turns out to be insecure, then all you have to do is just flip a configuration switch, and the system just moves to the other algorithm, and everything works fine. Now, in a client-server model, that actually is more difficult because you have to change both the clients and the servers. But we got to start somewhere. So, for example, if you build a web server, make sure that the web server can support multiple algorithms. Right? It's not baked in. The algorithm being used is not baked in somehow hardwired into the web server. When you build, a very common example is a software upgrade mechanism. So when you ship software upgrades to your clients, those software updates need to be signed, so that not anyone can ship an update on your behalf. Well, you cannot imagine how many companies, when they build software update mechanisms, they just hardwire RSA as the signature mechanism.
Right.
Yeah. And my point is, try to make it so that even like a software update mechanism, something as benign as that, actually is agile in the sense that there's easy way to update the algorithm on the fly, so that just a matter of simple configuration and boom, you move to signatures using a different algorithm. So that's the first piece of advice: be agile.
Yeah.
The second piece of advice is, in particular, when you build an SSL-based server. Today, many websites use what's called the RSA mechanism, which is the browser chooses a random pre-master secret, encrypts the pre-master secret using the server's public RSA key, and sends the results over to the server. The server decrypts and recovers the pre-master secret.
Yeah, this is what I taught when we covered how TLS works in its basic exchange.
Fantastic, fantastic.
Right.
So this is what I would call the basic RSA key exchange. The problem with that mechanism is it doesn't provide what's called forward secrecy. So what do I mean by that? Well, imagine that today someone recorded the interaction between you and the web server. So they recorded the RSA encryption of the pre-master secret. Now, a year from now, somehow they were able to break into the web server and recover the RSA secret key. What that key would allow them to do then is go back to what they recorded a year before, decrypt the encrypted pre-master secret, and now they can recover the entire session.
Game over.
Exactly. So the basic RSA mechanism doesn't have what's called forward secrecy. There is another key exchange mechanism in SSL. It's called it's a mechanism that supports forward secrecy, and that's a mechanism that's based on Diffie-Hellman. So there are multiple names for it. It's called ephemeral Diffie-Hellman. In OpenSSL, the name for it is DHE or ECDHE. We'll get to the differences between those in a second. And the idea there is that the key exchange actually uses the Diffie-Hellman protocol instead of using RSA.
Right.
So what happens is each side, the browser sends to the server its part of the Diffie-Hellman exchange. The server sends to the browser its part of the Diffie-Hellman exchange. And the server's RSA key, its only purpose is just to authenticate the server's Diffie-Hellman message.
It's just for signing.
So exactly. The server's RSA key is used for signing, not for encryption.
Yeah.
So even if the server's RSA key is stolen a year from now, it doesn't matter because.
And so forward secrecy means that even if somebody in the future cracks something, that I'm still secure going forward in time.
If the session was secure today, it will be secure a year from now, even if you lose your secret keys.
Right.
So forward secrecy it's a pretty important concept.
Yeah.
It's a good thing to do. Especially protects you from keys being stolen and such. It also limits the amount of time in which a particular key is used, because your session really now depends only on that particular Diffie-Hellman exchange.
Unlike with the RSA key, where the server has to get a new certificate, etc.
It's a whole process, takes a whole year. But the point is, if someone breaks your RSA key, somehow not by stealing the private key, but somehow by a brute force attack, if they break your RSA key, they would recover all sessions. With Diffie-Hellman, they would have to break every single individual Diffie-Hellman exchange to recover the session, which is a lot more work.
So it's clear going forward that network applications, the internet, are increasingly important. That more and more applications are just on the internet and are interconnected, and correspondingly, security is increasingly important. So in terms of classes going forward, what are the classes that that students could take to sort of learn more about this? Because in 10 years, not knowing something about security is going to make you dead in the water.
Exactly. Excellent question. So the security classes are kind of vital to undergraduate education in computer science. We get many complaints from industry about universities, not us, but other universities, graduating students who know nothing about security, and as a result, the code they write causes a lot of problems down the road. So the classes that we offer are one CS155. I would argue that needs to be a required class. So the point of CS155 is to teach you a lot of defensive programming, but more importantly, it's to get you into the security mindset. Right. And the way we do that is we teach you a lot of attacks. So the only way to learn how to defend against attacks is to know how to do the attacks yourself. So we teach you how to break things, but more importantly, we then draw lessons and teach you how to defend against those attacks and kind of get into the security mindset. Whenever you write code, think about how that code can be exploited and what will go wrong if the code is exploited. Okay, so kind of the security mindset, general principles for writing secure code, things like defense in depth, least privilege, and so on. These are things that we just go on and give many, many examples of those issues in CS155. So that's offered in the spring. It's co-taught by myself and John Mitchell. Another class that's worth taking is the crypto class, if you're more interested in learning how cryptography works. And I can tell you, the interesting thing is that there are many companies who actually use crypto, but they have very little crypto expertise. And so by kind of taking that class, you'll know what needs to be known about crypto in order to use it properly. And then whatever job you go to, you would actually become the go-to person at that company to deal with any crypto-like issues. So it's a valuable knowledge to have.
I'm convincing me I should go back to school. I haven't taken 155.
Okay, well, yeah, please do. Yeah, it's a fun class.
Great. Awesome. Well, any other last comments you think or thoughts about what's going on in security today and computer systems? Or
we could be talking about this for hours.
Oh, yeah, of course, it's DanBoneh. So.
I don't know. Do you want how long do you want to make this?
Well, why don't it be nice to these students, and they can in fact find out in 155 or 255. So thanks a lot, Dan.
See you in future courses.